This is Jeff Boggs presenting part 3 of the week 6 lecture for 2P21. When last I spoke to you, which for me was about 6, 8, 10 hours ago, I guess about 10 hours ago, 12 hours ago, we were in the middle of discussing ways to analyze numeric data. We talked about using numeric data to describe the distribution of a variable. We'd also talked about it as a way to compare two or more different groups, though in our example we just had two groups, so houses that were close, so within 100 meters of the railroad, and houses that were further than 100 meters from the railroad. But the third thing that we can do with numeric data is we can look for associations between variables. And so by an association, I mean a pattern, so kind of a systematic tendency for one variable to move in a particular direction, and as that happens, another variable moves either in the same direction or in the opposite direction. So if we proceed with the examples that we've been using, that is with the railroad scenario, we can talk about, we can ask a question, are newer houses further from the railroad? And based on our comparison in earlier slides, we think that this might already be taking place, but we want to see if this is how sort of systematic or how strong is this association. If our question is, are newer houses further from the railroad than our older houses, one way we can examine that, one way we can answer that question is to use something called a scatter plot. Scatter plot. So scatter plots require interval or ratio level data and what they do is they show us they allow us to see if there is a systematic relation between two variables. So both of the variables have to be either interval or ratio level, and this is our x-axis, and this corresponds, in this case, the distance of house from railroad. This corresponds on our data sheet to the variable called RRDIJ, so the distance from the railroad for house I, and I use DIJ just to familiarize you with some conventional notation that's used in geography to talk about distances. And then we have the age of the house, which I think is on the data sheet. We just call that the variable age, and that is our y-axis. So this whole thing is called a scatter plot. This line right there is a line of best fit. Line of best fit, and that is not necessary for a scatter plot. The only reason I added it is because it can help us kind of see the typical, I guess, the general pattern that's shown. But let's ignore that for a minute. Let's come back to each of these points. So each of these points actually corresponds to a single house. And this point in particular is the house that is at 74. So it's about 74 meters from the railroad. It's one of the closest houses. These are a little bit closer. And it is 56 years old. So in the notation of the Cartesian coordinate system, we could write that as 7456. So it is possible, actually, that you've already learned about in other courses, you've learned something called Cartesian coordinates. So just x, y coordinates, right? And what this tells us is that in general, so what the entire picture tells us is that as houses are further away from the railroad, they tend to be younger or newer houses. And I've also set up this particular scatter plot in this way so that the x-axis has what I suspect is the causal or the independent variable. So that's our independent variable, right? So we think that basically the distance from the house is what explains how old the house is. So age of house then is our dependent variable. And there's often a couple of other terms that people will use for these. So independent variables are sometimes called causal variables, and dependent variables, there's a couple of other terms, but it's early in the morning and they don't come to my mind right now, so we'll just skip that. So the main point then of all of this blah 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 is that we have a picture that shows us a pattern that we can use to answer our particular question. And in this case, this pattern that we see is one that indicates a negative association between, let me erase some of this stuff back here, a negative association between age and distance from the railroad. And so it's a negative association because as one variable becomes larger, the other variable becomes smaller. And Spickard has some examples of both positive and negative associations in the textbook, so you'll want to look at those to get a general sense. But in this particular case, we see that there's what we would call a weak negative association. And I know it's weak because I calculated something called Pearson's R correlation coefficient, which is something that you would learn in a stats course, Pearson's R correlation coefficient, which just gives you a single number that kind of sums up this pattern. And it's either, it's a number that ranges from -1 through to +1. But for our purposes in this course, we're not going to learn to calculate that. You just need to be aware of the differences between, a negative and a positive association, or no association as the case may be. Okay, I will stop this slide and we'll move on to the next one. Sometimes you don't have interval or ratio level data to look for associations between two variables. In those cases, you can use something called a cross tabulation. So the point here is that in addition to scatter plots, which require interval or ratio level data, we can also use cross tabulations, which usually focus on nominal or ordinal level data, at least for one of the two variables. Actually, you can have crazy cross tabulations with more than two variables, but we're not going to touch that for this course. So typically, crosstabs use nominal and ordinal data, though it could be that one of your variables is interval or ratio level, and you have to reduce it to ordinal level. That's acceptable. And we actually did that when, actually we reduced them to nominal level, I think. It would be more ordinal level in that case, even though our, if we think of our RR, our railroad variable, where it's a 0 or 1, that is a kind of ordinal level data, even though the numbering is a bit weird. So but what happened with our RR data is that we converted that ratio level data on distance, we converted it into ordinal data. Or some people would argue we converted it into nominal data, but I think it makes more sense to say it's ordinal data, even though it's just binary, 0 or 1. Okay. The thing about cross tabulations is that they need at least two categorical variables. So these are categorical variables is a term for nominal or ordinal level variables. So we can make age an ordinal variable in our example. So we could say houses that are built in the last 50 years fall into one group. So for instance, if we count the number of houses that are 50 years or younger, according to my calculations, there were 9 of those. 1, 2, 3, 4. Hold on, let me start again. Okay, so 14, 25, 18, 13, 19, 1, 2, 3, 4, 5. There's 5. There's one that's 39, that's 6, 39. There's one that's 21, that's 7. There's another one that's 47, that's 8. And another one that is 35, that is 9. Yeah, so there are 9 houses that are 50 years or less in age. And then we can put all of the other houses, so the houses that are built over 50 years ago, into the second group. And an easy way to calculate that is, well, we could go through literally and count them, which isn't a bad idea, or you can have software do it. But if there are 33 observations and 9 of them are 50 years or less, then 33 minus 9, we should have 24 houses that fall into this second group. And let me just see our notes. Yep, so more than 50 years. So N, our sample size in that case, is 24. And you'll notice that I have a lowercase n. A lowercase n means that's shorthand for sample size. So in some of the papers that you were reading, you might have seen this attached to some of the tables, or in explanations of the data. So it would say something like, n equals 37 or n equals 423. And if it's a lowercase n, so a Latin n, lowercase, that's denoted by a lowercase, that means that it's a sample size. So the lowercase letter n. If it's a capital N, that is the population size. So that's that's how many elements are in that population. So in our example, we don't actually say what the population size is. But, it would be larger than 33. Because if the population size were exactly 33, then what we would really have is we wouldn't have sample data, we would just have a census. We would have counted all of the houses. But I digress. The point of this slide is that if you have interval or ratio level data, that you can reduce it to ordinal variables very easily. Though when you do that, you lose some information. Okay, let's go to the next slide. We can then combine this with the other ordinal variable railroad, which actually we've already converted. So houses within 100 meters of the railroad receive a 1. And actually there were 9 houses within 100 meters of the railroad. And again, we can check this for ourselves. So to do that, we would go to the RRDIJ variable and count the number of houses that are 100 meters or less. So we've got 99, 99, 95, 74, 68, 32, 25, 36, 79, 65. So that's 9 houses. Which then, by the amazing power of deduction, it means that there should also be 24 houses that are beyond 100 meters from the railroad. And so those houses we gave a 0. So we should have 24 of those, right? And 24 plus 9 equals 33. We always, want to be able to add up all of these observations to come up to our total sample size as a way to check our work. And you might be wondering, how is this an ordinal variable? It's scaled backwards. If I were going to go back and redo all of this stuff, I would reverse. I would make, if it's within 100 meters, I would give it a 0. And if it's over 100 meters, I would give it a 1. But originally when I designed this handout, and this one says it was created in October of 2018. This is actually based on a much older example that I've used in stats courses before that's probably closer to 10 years old. So I did not score this in a way that might make the most sense to you. Except, if we think of 0 as far and 1 as near, maybe that'll make more sense. But in any case, that's not such a big deal here. The next thing that we want to do when we are making a cross tabulation is that we have to recall that a cross tabulation is it's a table. So the first thing that we do is label our table. So on one axis, we have 50 years or less and more than 50 years. So this axis across the top, if you will, you can think of this as our x-axis, I suppose, in this particular instance. We have, all of our observations are either less than, or are either 50 years or less, or more than 50 years. And all of our observations are also, over 100 meters from the railroad or within 100 meters of the railroad. So we make a little table that looks like this. Over here, we have what's called the row total. So this, give me a second here. The thing to remember is if we think of this cell as A and that is B, then our row total should be A plus B. And if we think of this as C and this as D, then our row total over here should be C plus D. And so remember, rows go across. Columns are like columns in a building. They hold up the ceiling. They go up and down. And so our column totals, so for this column, it's A plus C. For this one, it's B plus D. And then our row total should just be all of these together. So it would be A plus B plus C plus D. That looks like hell. Let me fix that. So A plus B plus, well, fiddlesticks, plus C plus D. There we go. This gives you kind of a sense of the layout for a cross tabulation. So after we make the table this way, then we have to populate each of these cells. Having made our table, hold on, we now want to fill in the counts for each of these cells. And you can do this manually, which takes some time, or you can use some software to do it, which has the added benefit of being less likely to make dorky mathematical mistakes where you space out and forget to count something. So we see that there are 7 houses that are less than 50 years old, but over 100 meters from the railroad. There are also 17 houses that are over 100 meters from the railroad and more than 50 years old. There are 2 houses that are 50 years of age or less and within 100 meters of the railroad. And then there are 7 houses that are close to the railroad, but also older than 50 years. So these are the cells that we have populated by sort of going through our table, figuring out, how many houses fell into each of these into each of these 4 categories. If you think in terms of Venn diagrams, you could think of this as like this is the union between 50 years or less and over 100 meters from the railroad. So that would be this cell. This would then be, this cell is the union of more than 50 years age and over 100 meters from the railroad. The Venn diagram for this cell is then 50 years or less and within 100 meters of the railroad. And the Venn diagram for this one is more than 50 years and within 100 meters of the railroad. We then want to add to get our row and our column totals. So there are 24 houses that fall into within 100 meters of the railroad. There are 24 houses that are over 100 meters from the railroad. There are 9 houses that are within 100 meters of the railroad. There are 9 houses that are 50 years or younger, and there are 24 houses that are more than 50 years. And this is just sort of happenstance that it says 9 and 24 and 24 and 9. This doesn't always happen. It just depends upon the vagaries of your sample. So don't expect to see, some strange pattern like this in every scatter plot. When we add 24 and 9, we get 33. We add 9 and 24, we also get 33. So your column total should be the same as your row total when you add all of these 2 columns together or these 2 rows together. So that's a way to check your work. The next step then is to convert these counts to proportions or percentages, because that's often easier to read or to make sense of. So we have our table. We have, in this cell, we had 7 houses that were both 50 years or younger and more than 100 meters from the railroad. So 7 divided by 33 gives us 0.212, or 21.2% if you think in terms of percentages. For this cell, more than 50 years and over 100 meters from the railroad, we see that there are almost 52% of all the observations fall into that category, so 0.515. Within 100 meters of the railroad and less than 50 years, we see that it's 0.061, or just a little over 6% of all the observations. And this last category, more than 50 years and within 100 meters of the railroad, there are 7 houses that fall into that category out of the 33 total houses in our sample. And that is 0.212 is the proportion, or 21.2%. The benefit of converting these to proportions is that, or to percentages, actually, depends. Some people are more comfortable with percentages than proportions, but they tell us the same thing. The benefit of this is that it allows us to say, out of all of the observations, what percentage of them or what proportion of them fall into each of these 4 categories. We also do this with the row totals. So we had 24 that were over 100 meters from the railroad, so 0.727, or almost 73%. And then we had 9 that were within 100 meters of the railroad, so 0.273, or just a little over 27%. So almost 3/4 of the houses are more than 100 meters from the railroad, and a little bit over 1/4 are within 100 meters. We repeat this then for the columns. So in this column, we had 9. So 7 plus 2 gives us 9. And we actually saw this before in the previous tables. So 9 divided by 33 gives us 0.273. And repeat that over here. 17 plus 7 is 24. 24 divided by 33 is 0.727. So we see also that most of the houses, almost 3/4, are 50 years or older, and only a little bit over 1/4 of the houses are 50 years of age or younger. When we add 0.273 and 0.727, either across the column total or across the row total, 0.727 and 0.273, it should come up to be 1. Also, if you divide 33 by 33, you should get 1. Another thing to bear in mind, this is useful for checking your work if you find yourself doing this stuff by hand, is that if you add this and this and this and this, those 4 proportions should all equal 1. Having converted our counts to proportions, we now have the data that we can look at to try to get an answer to our question. And first of all, the big pattern in this, or the pattern that's of most interest given our original question, so I think it was R, and R in that case is A-R-E, in case you can't understand my accent. So our houses are younger houses further from the railroad than older houses looks to be yes. So we know that there are, in terms of houses that are 50 years or less, there's only 9 of them. And most of them, 7 of those 9, are found over 100 meters away from the railroad, whereas only 2 of them are found within 100 meters of the railroad. But also, if we look at the older houses, and the thing to pay attention to is that almost 3/4 of our houses are older, using this definition up here of more than 50 years. So almost 3/4 of the houses are older. And most of the houses actually are more than 100 meters from the railroad, or most of the older houses are. So 17 out of the 33, or actually 17 out of the 24, but we're not going to get there. That most of the houses are older and further away, but if we look, so we're interested in this notion of, closer to the railroad. Closer to the railroad. For that, we really want to look at this. So, of the houses that are within 100 meters of the railroad, how many are there? So there are 9 houses within 100 meters of the railroad, and 7 of those 9 houses are more than 50 years old. Whereas only 2 of them are less than 50 years old. And so that's one way to think about that. And then if we look at just the younger houses, there's 9 of them, and only 2 of them are actually anywhere, within 100 meters of the railroad. So this then suggests that older houses tend to be closer to the railroad than our younger houses. And this can often be kind of messy to work through. There are statistical tests that can go along with this, like a chi-squared test is one example, but we're not going to go there today. What I wanted to do was just to help you think about how these kinds of tables can be useful for helping us understand kind of general patterns in our data and for looking for associations. So even though most of the houses are over 50 years old, so we know that from over here. So most of the houses are over 50 years old. And most of the houses are over 100 meters from the railroad. Once we then start to control for whether or not it's an old house or a young house. So young, if you will, or new and old. And then whether or not it is far away or close, then we can start to answer our original question. And in general, what this suggests is that older houses tend to be closer to the railroad. I just want to end this by saying that, at least this portion, to say that scatter plots and crosstabs are often the easiest way to identify associations between 2 variables, and leave it at that. And before I end this lecture, I just want to cover fallacies that Spickard identifies that are common when people analyze numeric data. I think only one of these is an actual proper logical fallacy, if you know what those are. But for now, let's just sort of go with what Spickard has. So he talks first about something called an ecological fallacy. And that is when you generalize outside your original unit of analysis. A famous example of this was critiques of Durkheim's work on suicide. So Durkheim's book, I think, was called Suicide. And it was written in, I think, the 1890s or the early 1900s. Durkheim was an early sociologist, and he had data on suicides by location in different parts of France, actually maybe even different parts of Western, what we would now think of as Western Europe. And the problem was that he was then saying that people from certain, individuals from certain locations were more likely to commit suicide based on these data, even though they weren't individual level data. They were actually, and this gets back at the difference between, unit of analysis and unit of observation. So that his units of observation were basically, geographical units, so like regions, parts of countries. And he was then making claims about individuals in those countries, even though he didn't have individual level data, he just had regional level data. And Spickard goes on to provide a much more well-rounded explanation of this, so you want to have a look at that. But if you are a geographer, you especially want to pay attention to these because you use area data a lot. And actually, tourism studies, a lot of people use area data as well. So you just want to make sure that you're not generalizing outside your original unit of observation and analysis. There's something called a sampling fallacy, which is kind of his own term. What he means by that is you're generalizing from a non-random sample. So remember, in the first part of the lecture for this week, we talked about the differences between random and non-random sampling. So just, if you have a non-random sample, you cannot generalize to the larger population. If you do that, that is a sampling fallacy in the way that he describes it. There's another term that he's come up with called significance fallacy, and we haven't talked about significance tests, though in the readings he does say a bit about it, but I think this is probably more appropriate to leave for a proper stats course. But the gist of it is that you're claiming that there's a difference when there is no statistically significant difference. So the thing to remember about samples is that they are, if they're from a random sample, is that they are the best estimate we have of the actual population parameter or characteristics. So, in our case, we had age for our sample, and it was, I want to say it was 62.7 was the mean. But this is actually a sample mean. So that's our sample mean. We don't, and that is our best estimate of our population mean. But actually, that 62.7 will also then have some margin of error around it. And we haven't gone into calculating that. But it could be that, our margin of error is, plus or minus 3 years. And what that really means is that, our best estimate, this is called a point estimate. So our best estimate isn't really this point. Instead, it is an interval of 62.7 years minus 3 at the lower end. So 62.7 minus 3 is, I want to say 59.7. So that's our lower bound. And then our upper bound would be 65.7. Actually, let's go back here. Let's get rid of all this stuff. There we go. Get rid of all that. Make that go away. So our, there we go. No, hold on. No. So our best estimate, if it is plus or minus 3 years, is actually, let's write this in darker blue, would be 59.7 years to 65.7 years. Indirectly, what he's talking about is the significance fallacy is related to the fact that people often forget that our sample means are really just point estimates, and that when we're talking about something like statistical significance or statistically significant differences, is that we're actually talking about a range around that point estimate. And it could be that, if we were looking at another location and its range was, 60 to 67 years for a different population, that these two ranges actually overlap. So 59.7 extends a little bit further to the left of 60, and 65.7 extends a little bit, or doesn't reach as far as 67. But the point is that these two intervals overlap with each other. And if that's the case, then that suggests that there's not a statistically significant difference when you are comparing two, in this case, it would be two sample means. So once we took into account, maybe the mean for this one was 63, and then, it was going to be plus or minus, or 63.5, and then it was going to be plus or minus 3.5 years. Okay, so I'm probably belaboring this point. This isn't something you really need to pay much attention to at this stage in your career, but in a stats course, you'll learn more about that. And he then, Spickard, comes up with this wacky term, significance fallacy, that's a useful shorthand for kind of explaining this, or for remembering this common problem. I think that is everything. Thank you for toughing it out and listening to all this blah, blah, blah. And I will see you next week.